So in this video, we're going to take a little bit of time to talk about what's called the law of sines. So we've done some work over the past few videos with right triangle trigonometry. We've done some work with the Pythagorean theorem. Both of those ideas apply only to right triangles. What's cool about the law of sines, and you'll see that in this opening sentence it says it, the law of sines applies to any triangle. So it doesn't have to be a right triangle, it can be any triangle. So we're going to have triangle ABC be any triangle. Lowercase a, b, and c are going to represent the measures of the sides. And then the opposite angles are going to be measured with the corresponding letters, but the capital versions of them. So if you look at my diagram here, we should be able to make decent sense out of what that sentence really said. Here's side lowercase a. The angle that's opposite that side is going to be labeled with capital A. And you see that lowercase c and capital C are opposite of each other, and lowercase b and capital B are opposite of each other. Then this equation is true. Now, this is a three-part equation, and depending on your textbook, on your teacher, on your professor, you might see an alternate version of this than what I'm showing. You might have the signs in the numerators and the sides in the denominators. So there are multiple versions of this. I'm just showing you the one that the textbook that my current class is working out of has within it. So if I take side A and I divide by the sine of angle A, that fraction has to equal side B divided by the sine of angle B, and that also has to equal side C divided by the sine of angle C. In another video, we're going to kind of show why this is true, so we're going to do a derivation for this. But in this one, we just want to kind of look at it, practice with it in an example, and that's about it. So we're just introducing it within this video here. So again, big point to make, it applies to any triangle, not just right triangles. So this kind of breaks down a barrier that we've had sitting in front of us for the past few lessons, and that's we could only do the trig that we've been looking at on right triangles. Now the law of sines is able to be applied to any triangle. Keep in mind how you have to label the sides and the angles though, right? The sides have the lowercase letters, the angles have the corresponding capital letters, and the angles and sides that correspond to one another are on opposite sides of the triangle. So we'll go ahead and we'll look at a quick example here. So we want to solve triangle ABC, and solving triangle ABC means to find any of the missing angle measures and side measures that you don't know. In this video, we'll just, to keep it short, we'll just kind of show one quick application of the law of sines, talk about how to get the rest, even though we won't necessarily see them done within the video. So I have my triangle drawn. Now, your triangle doesn't have to be labeled perfectly. I have these angles given, 33 degrees, 105 degrees. The nice thing about having two of the three angles of a triangle is you know that the third one has to add on to the sum of the prior two to get to 180, right? All of the angles have to add up to 180 total. So if you just do 180 minus 33 minus 105, that's going to give you this missing angle down here, and that would be angle C, right? So the capital letters represent the angle measures, and then the lowercase letters represent the side measures. We do have one side measure given here. It's for side B. It tells us that side B is 37.9 units. So if I'm labeling angle B up at the top here as 105 degrees, I have to label side B on the other side of the triangle, on the opposite side. So angle B, side B. Here's angle C, side C would be over here. I don't really know why I left that off. Maybe I can go ahead and label that real fast. Might look a little bit ugly because I'm working with my mouse and not at the board. Looks okay. And then I have angle A, and then opposite that I have side A. So what we're going to look at here, we already talked about how to find that missing angle. That's not a big deal. That works for any triangle. All of the angles sum to 180 degrees. So that was easy enough to find. We have two things that we still have to find. We have to find side A, we have to find side C. So we're going to find side A. So what I did is I used the first fraction within that three-part equation, and that's side A divided by the sine of angle A. So I'm building that fraction. Now I don't know what side A measures as, so I still have that represented as the variable lowercase a. and then I'm dividing that by sine of 33 degrees, right? The way that you construct these fractions has to be appropriate. If this is the side A, I have to use sine of the angle that's opposite that side when I build the denominator of that fraction. And opposite side A, we see a 33-degree angle. I'm going to set that equal to another fraction here. I've got an option with what I do. I can either set it equal to this fraction involving side B and angle B, or I could set it equal to this fraction involving side C and angle C. Now think about what we have access to and what we don't have access to. I see people who, when you have options, they tend to get overwhelmed by the variety of options that sit in front of them, and they might kind of give up and close up shop. Definitely don't do that. We've got options. I've already built this fraction. I want to find side A. You'll see what I already have written here. I used side B, right, 37.9 units, divided by the sine of angle B, which was 105 degrees. Should be pretty obvious why I did that. If I was building this fraction, side C divided by sine of C, I do know angle C, but I don't know side C. So if I had a capital C, or excuse me, a lowercase c right here for side C divided by the sine of 42 degrees, I would have this one equation built, and I would have two unknowns within that one equation. And to solve for two unknowns, you need at least two equations. So that's not something that is wrong to do, but hopefully you realize why it's not useful to do at this point in time. We want to build this second fraction, and I guess I didn't have to build it second. It could have been the first fraction I built. We're going to build one of our fractions by utilizing the angle and the side opposite of it that we know in their entirety. So to solve this for side A, I'm going to have to undo this division. So I'm going to multiply this fraction by the sine of 33 degrees. If you're careful, you can break out the calculator at this point, and you have to make sure you're in degree mode. We're measuring in degrees right now. So as long as you're in degree mode, if you type this in, rounded off to the nearest tenth is 21.4 units. So that would be for side A. Now to find side C, I would have to go through a similar sequence to what I did right here. I would honestly urge you to use this fraction again when you find side C. So basically, just change the left side of this equation. So lowercase c divided by sine of 42 degrees, and then do a similar sequence to solve for side C. The reason why I would avoid building this fraction with that answer in place of A, this answer, if you did take time to type this into your calculator, this answer right here, 21.4, it is rounded off. If I continue to do more math with an answer that's already been rounded off, I'm not going to lose a ton of accuracy, but I'm going to lose some accuracy. So just to avoid that round off there, if we use the components that we didn't have rounded off at all because they were provided to us from the beginning rather than something that we computed along the way and rounded off ourselves. That's just mathematically speaking a little bit better practice to go with. Use the values that are not rounded off and then round off that result to the desired degree of accuracy that your problem, your teacher, your professor is requesting of you. So we'll do a few more examples of these. Eventually, this is going to ramp up. We have to talk about what's called the ambiguous case for the law of sines. This is just kind of a tailor-made introductory example to the law of sines. We'll do some more with law of sines in the next handful of videos.